Hi everyone, welcome to the 34th season of the Mt Tam Astronomy Program presented by the Friends of Mt Tam. My name is Neeti Sonth and I am the webmaster of Mt Tam. I'm honored to represent Tinka Ross, the illustrious founder of the Mt Tam Astronomy Program. I request everyone to hold their questions till the end of the presentation. You can unmute yourselves to ask a question or paste the question in the chat, and hopefully I would do a good job of reading it for you. All right, it's my pleasure to introduce tonight's speaker, Dr. Imke de Pater. Imke de Pater is a professor emerita and professor of the graduate school in the departments of astronomy and of Earth and Planetary Science at the University of California at Berkeley. She studies planets using telescopes at visible to radio wavelengths. She started her career observing and modeling Jupiter's synchrotron radiation, followed by detailed investigations of the planet's thermal radio emission. Over the past 2 decades, she has exploited adaptive optics techniques in the infrared range to obtain high angular resolution data of, example, volcanic activity on Io, weather on Titan, planetary rings, and the giant planets. She's flown on the Sophia airplane and used the upgraded Very Large Array on the Atacama Large Sub-Millimeter Array to map the atmospheres of the giant planets. She is the PI with Thierry Faucher of a successful JWST ERS, Early Science Release Proposal. Professor Imke de Pater has written 2 books together with Jacques Lesueur on Planetary Sciences, publisher Cambridge University Press. Finally, she's received a number of prestigious awards during her career and is a member of several international committees. Please welcome Professor Imke de Pater.
Okay, so I will talk about Neptune. Neptune, the planet Neptune was discovered about 175 years ago, or approximately 1 orbit of Neptune around the Sun ago. So it was Johann Galli who discovered the planet in September 1846 using the Fraunhofer telescope, which is now at the German Museum of Munich. So the past 30 years, we have learned a tremendous amount about Neptune, starting with the Voyager spacecraft in 1989, and then followed by the Hubble Space Telescope and the 8 to 10 meter telescopes like Keck and the VLT in the visible and the infrared. And then also the Very Large Array and ALMA at radio wavelengths. So in this talk, I will summarize the story of Neptune from its discovery to the present to essentially celebrate its 175th anniversary, albeit a bit late. So, but before embarking on this story, let's talk a little bit about why we're interested in Neptune. So we can tie this to the overarching question where we humans come from, which starts with the quest to how our solar system formed out of its protoplanetary disk. And in order to unravel that, we need a detailed characterization of all the bodies in our solar system. So Uranus and Neptune are particularly intriguing because many exoplanets that have been detected so far are roughly in the size and mass range of these planets. So their formation and evolutionary history may hold keys not only for our own solar system, but also for the formation of planetary systems in a more general way. So one important ingredient for formation models is composition. So we refer to Uranus and Neptune as the ice giants, in contrast to the gas giants, Jupiter and Saturn, since they are composed mostly of what we call fluid ices, in particular water, in contrast to the gas giants, Jupiter and Saturn, which are much closer to a solar-like composition. So heavy elements, where we mean carbon, silver, nitrogen, oxygen, phosphor, which on the giant planets are present in the form of methane gas, hydrogen sulfide, ammonia, and water, are very close to solar in Jupiter and Saturn. With on Neptune and Uranus, they are enhanced about 50 times above solar. And so we know this through observations at different wavelengths, which I will show you later. So as part of our solar system's formation theory, we also need to understand the formation of rings and moons in orbit about these planets, including those of Neptune. So in this talk, I will start with the discovery and early history of Neptune. And then I'll talk a little bit about its moons and rings, about Neptune's great dark spots, and Neptune's atmospheric structure as derived from multi-wavelength observations. And then I'll talk a little bit about large convective storms and also the amateur community, what role they played in this. And then I'll end with the long-term evolution of Neptune's atmosphere. So after William Herschel discovered Uranus in 1781, observations showed irregularities in its orbit, and that was soon attributed to the potential presence of yet another planet. And this sketch here shows that the inner planet, Uranus, will be sped up in its orbit in position A and slowed down in position B due to the gravitational force from a planet further away that orbits the sun much slower. So both Adams in England and Leverrier in France were determined to calculate the position of this putative planet unbeknownst to each other. Leverrier sent his coordinates to Johann Galle at Berlin Observatory, who found the planet within 1 degree from the position that Leverrier had predicted. So after 2 more nights of observations to check its position and motion, Galle replied to Leverrier, "The planet whose place you have computed really exists." So in retrospect, the first observations of Neptune, however, were made by Galileo Galilei in 1612, when he observed Jupiter and its moons. But unfortunately, he did not recognize that the star as a planet, which is shown here in 1612. Here we see the star, and in 1613, we see this star over here. So he didn't recognize that, but when we compare that to the sky at that time, as obtained using the Starry Night software, we can see that really he had observed Neptune instead of a star in both cases. And similarly, yeah, so in both cases, months apart. So then only 17 days after the discovery of Neptune, William Lassell discovered Neptune's largest moon, Triton. And the orbit of Triton, which is shown here in purple, is opposite in direction and tilted by 23 degrees compared to a typical moon's orbit, which is in blue, in the plane of Neptune's equator. So moons in retrograde orbits cannot form in the same region of the solar nebula as the planets they orbit. So Triton may have been captured from elsewhere, and I will get back to that later. So, and then we wait another 100 years before Gerard Kuiper discovered a second moon in orbit about Neptune, which is Nereid, in a highly eccentric but a prograde orbit in Neptune's equatorial plane. So we now know that all 4 giant planets have rings, and in some cases, rings were discovered via stellar occultation events, like shown here for the Centaur Curriculo. When the star gets occulted by a ring, a dip in its intensity is seen, the light disappears completely when the planet itself occults the star, and a second dip is seen when the ring occults the star upon egress. So interestingly, in 1984, when Neptune occulted the star, a dip was seen for about a second upon ingress before Neptune occulted the star, but not afterwards. And this one-sided occultation was interpreted as Neptune having a ring arc rather than a complete ring. So our view of Neptune was completely changed when the Voyager spacecraft encountered the planet. So the iconic image of Neptune with its great dark spot 2 and Scooter captivated astronomers and the public alike. So the great dark spot, which is seen here at the center, is about as wide as the Earth is. So the early discovery of a ring arc was confirmed by exquisite images taken by Voyager 2, which showed 4 arcs, Fraternity, Égalité, Liberté, and the leading arc, Courage. So then stunning images really of the satellite Triton were obtained, which revealed this enigmatic cantaloupe terrain and a hemispheric scale polar deposit or cap around the South Pole. The surface is extremely young, less than 100 million years for sure, but maybe even perhaps less than 10 million years. The polar cap is thought to be predominantly nitrogen ice, and a few of these dark spots are geysers, 8-kilometer high geysers, tens of hundreds of kilometers long. So Triton is only slightly larger than Pluto and nearly identical in composition, and that has led to the hypothesis that they share a common origin, and that Triton in fact originated in the Kuiper belt and was captured by Neptune. This would explain its retrograde, highly inclined orbit, and its capture may have changed Nereid's orbit into the eccentric orbit that we see nowadays. So in addition to ring arcs, rings and geysers on Triton, the Voyager images revealed 6 inner satellites, which increases in size monotonically with distance from the planet, from little Naiad, closest to Neptune, up to the largest moon Proteus, which is about 400 kilometers across, and Naiad is about 60 kilometers across. So several rings were also discovered, as shown here, and they're all named after people who discovered Neptune and its moons in the early history, like Gally, Leverrier, and Adams. So the moon Hippocamp, which is indicated here, was discovered only a few years ago in 2019 on images taken with the Hubble Space Telescope by a group led by Mark Showalter. So Hippocamp orbits very close to Proteus, the outermost and largest of these moons. So Hippocamp is about 10 times smaller than Proteus, which is shown here in this HST kind of movie. Hippocamp is circled in red. Proteus has migrated outwards because of tidal interactions with Neptune. And our results suggest that Hippocamp may be an ancient fragment of Proteus, providing further support for the hypothesis that the inner Neptune system has been shaped by numerous impacts. This scenario is supported by Voyager images that show a large impact crater on Proteus, almost as large enough to have completely shattered that moon. So we observed the rings several times with the Keck telescope, a 10-meter Keck telescope in Hawaii, and noticed that the 2 leading arcs were slowly fading away. Now, in order to build up sufficient signal to noise in these images, we had to add many images together, and that is shown here. I don't know if you see my pointer, but the moons here in orbit about Neptune show up as little short arcs because they are, of course, orbiting Neptune while we are taking images. The ring arcs themselves also orbit the planet, and so we had to deproject each image and shift them to stack the images of the ring arcs, as shown here for the Adams and Leverrier rings in 2003 and 2009. So below here, we show scans through these ring arcs, through the rings. And we can see here the one taken during the Voyager era shows very nicely the ring arcs Fraternity, Égalité, and Liberté and Courage. However, in 2003, we already see that the leading arcs, Courage and Liberté, have decreased a lot in intensity, and in 2009, they're completely gone. None of these leading arcs are visible, while the trailing arcs are still there. So images taken with the Hubble Space Telescope in 2016 also show that the leading ring arcs have disappeared. So this last October, we participated in a campaign to observe an occultation of a star by Neptune. Well, unfortunately, the Keck telescope does not have the ability to record images at a high time resolution. I mean, we really need a resolution of about 100 to 200 milliseconds, because it took about a second for a ring arc to move over a star. So our time resolution was only 10 seconds. Some other telescopes do have high time resolution, like the Large Binocular Telescope and Palomar, both equipped with adaptive optics system. So for any occultation experiment, we really need a high time resolution and ideally also adaptive optics. So all the data still have to be reduced. So we were able, however, to construct this gorgeous image here, which is in the so-called H band at 1.6 micron. We averaged 30 images, just like in the previous slides, and then we high-pass filter to get rid of Neptune's scattered lights. So the moon show up again as trails, and similarly the ring arcs are smeared out. So this will all take some time to process before we really know what the ring arcs will look like. But this image will be tremendously helpful for the occultation experiments that we have done. So one of my students, Ned Malter, wrote a computer program to look at the moons. That is, he took all these 30 images and centered them on a moon using the coordinates as provided by the Jet Propulsion Lab. The results for some of them are shown here, and you can even see, well, on a computer screen it might be hard, but you can even see the so-called diffraction pattern of the telescope. The little one, Naiad, was a moon that wasn't seen for a long, long time since its discovery by Voyager. But finally it was recovered in Hubble Space Telescope data. It's the same data where we discovered Hippocamp. Our Keck data of Naiad are in fact the first detection of this moon at infrared wavelengths. And this may tell us a lot more about its composition, and similarly for the other moons. And I show here Despina and Galatea. So let's return now to the planet Neptune itself. So the first images from Hubble Space Telescope showed that Neptune's great dark spot had disappeared in the early 1990s. So new dark spots were discovered in the Northern Hemisphere with HST in 94 and 96. Well, the third time a dark spot was seen since the Voyager-era was 20 years later in 2015, again with HST, but this time at southern latitudes. And then a really large, long-lived one was discovered in the far north in 2018. So this one is still visible as of a few months ago. So here's an image from January 2020, where we saw also some transient dark spots. These were not always seen. Here's an image from 2021. And our most recent image is from January 22, but that has not yet been processed into a nice figure. So as shown, initially, there were a lot of clouds around these dark spots, perhaps orographic clouds, like clouds around mountains on the Earth. But in 2020 and 21, we do not see any clouds. And I will get back to that very interesting phenomenon later on in the talk. So such dark spots can only be seen at blue wavelengths around 450 nanometer. So we can only do this with HST at the moment, and we have to wait for adaptive optics at visible wavelengths before this can be done from the ground. So the great dark spot in the Voyager-era migrated north, it was in the south, migrated north towards the equator. And it probably was disrupted when it came close to the equator due to the vanishing Coriolis force at the equator. So this new dark spot, the 2018 one, also migrated in the direction of the equator, as shown in the top two panels, perhaps oscillating a little bit in latitude. Transient features here were seen on several occasions, and they are indicated by the pink symbols. Perhaps these are flaking off the storm, we don't know. While migrating, the storm got rounder, that is, its major axis decreased, which is different from the great dark spot where the minor, the north-south axis grew in extent. So predictions are that spots disrupt when they get closer than about 15 degrees or so from the equator. And this particular dark spot is very close. However, it still persists, at least until a few months ago. So based upon the zonal velocity of dark spots, so the winds, or basically the motion of the dark spots, they appear to be anchored deeper in the atmosphere than the bright clouds that we see. So Pat Irwin recently suggested, based upon radiative transfer calculations that match spectroscopic data, that the dark spots may be dark caused by a clearing in a lower cloud layer, the so-called hydrogen sulfide ice cloud. And we'll get back to those cloud layers later on as well. So the Keck telescope came online in 1993, the first of the 8 to 10 meter telescopes. So we initially used a technique known as speckle imaging to obtain high spatial resolution images. Basically, that is just taking a lot of images at sort of speeds of 100 to 200 milliseconds. Many of the amateur astronomers use the same technique nowadays. So these images here showed large, bright storm systems on Neptune. So, I mean, this is neat, but what can we actually learn about the planet to bring us closer to our goal of understanding its composition and atmosphere? For that, we really need to use observations at different wavelengths and, if possible, spectroscopic data. So at different wavelengths, we probe different depths in Neptune's atmosphere, as sketched in this busy diagram. Shown are the temperature pressure profile in black, which is shown over here, and the tropopause bands at the temperature minimum here in yellow, near 0.1 bar. And based upon Neptune's composition, which is derived from such multi-wavelength data, we expect the following cloud layers in the atmosphere. If we start in the deep atmosphere, we see a water or solution cloud, that is water with some other elements dissolved into it. Above that, we have the ammonia hydrosulfide cloud, and this cloud forms from combining one molecule of hydrogen sulfide with one ammonia molecule. And hence above this cloud, we only have hydrogen sulfide or ammonia gas left, whichever one is most abundant. And that is hydrogen sulfide on Neptune and Uranus, and ammonia gas on Jupiter and Saturn. So above this NH4SH cloud, we find this H2S ice cloud, and the top layer is methane ice. And so the hydrogen sulfide ice cloud, that is the cloud where Pat Irwin thinks it kind of dissipated in part, which gave rise to the dark color of the dark clouds. So in the visible and the near infrared, where we receive sunlight reflected off clouds, aerosols, and gases, we probe altitudes around the tropopause down to the cloud layers, as shown by the various arrows here. In the mid-infrared, where we receive thermal emission from the atmosphere, we probe levels in the stratosphere above the tropopause from about 1 millibar down to the top of the cloud layers. And then at millimeter and centimeter wavelengths, using ALMA and the Very Large Array, VLA, we receive the planet thermal emission from below the cloud layers down to within the NH4SH clouds. So by using data at all these different wavelengths, we can determine the composition of Neptune's atmosphere. And that is very different from that of Jupiter, Saturn, or the Sun, shown here. What we see near the cloud layers, however, also depends on the general circulation in the atmosphere, which we can in turn derive from the data. But so as shown here, and I'll get back to that later on too, is that we have about 80% of hydrogen, 15% of helium, and then methane gas is about 80 times the solar carbon abundance. Hydrogen sulfide about 40 times. Ammonia is about equal to the solar nitrogen abundance. And water, we just have no idea. So as I will show you later in this talk, most of our observations suggest a circulation model as sketched here, where air is rising at mid-latitudes from the deep atmosphere near the NH4SH cloud layer through the hydrogen sulfide and methane clouds up into the stratosphere and descending over the equator and the poles. So it might be helpful to have seen this now before I explain how we actually have derived this. So our early adaptive optics images from Keck were taken with the NIRSPEC spectrometer with its imager scan. And we still use that instrument nowadays, but it has been upgraded tremendously since then. So by placing the spectrometer slit as shown here, sideways on Neptune, we can also position it like shown here in the inset, when we can look or take spectra of different cloud features. So these spectra that we take here are between 2 and 2.3 micron, and hydrogen and methane are absorbing very strongly between 2.1 and 2.3 micron as indicated. If a feature is deep in the atmosphere, it will be very dim at these wavelengths, since most sunlight on the way down and up through the atmosphere is absorbed. If there are no clouds, like near the equator, the red line at the bottom is very low in intensity. Feature 3 here in the far south is also deep in the atmosphere, but so it's bright initially at near 2 micron, but it's very dark between the 2.1 and the 2.3 micron. So when we look at features near the pole and southern mid-latitudes, we see that they must be much higher in the atmosphere since they are much brighter between 2.1 and 2.3 micron, like black and the green lines. So this image in the lower left shows visually where we see the clouds. So red clouds basically in the north and at mid-latitudes are at high altitudes, and white clouds further in the south are deeper in the atmosphere, in particular this cloud feature in the far south. So in 2003, we devised a multi-wavelength campaign to determine this global circulation pattern in the atmosphere and, of course, the composition of the atmosphere. We used Keck to image Neptune in many narrowband filters to determine the altitudes of 17 cloud features, as indicated in these images here, using radiative transfer calculations. So we typically probe the region above and below the tropopause, as indicated. As just shown, clouds in the north are all in the stratosphere, so high up. At mid-latitudes, we see kind of 2 levels, some in the stratosphere and some in the troposphere, below the tropopause. And the south polar features are the deepest. So the few faint clouds that we see near the equator are near or just below the tropopause. So many clouds that we see in the troposphere are located near where we expect the methane ice clouds, and they're therefore likely composed of methane ice, while clouds in the stratosphere are probably hydrocarbon hazes. So at mid-infrared wavelengths, where we receive thermal emission, we probe the stratosphere. So at each wavelength shown here, we are sensitive to different gases and probe slightly different altitudes. So for example, at 8 or 8.9 micron, we are sensitive to methane gas. At 12 micron to hydrocarbon ethane, and at 18 micron to hydrogen gas. So as shown, the pole is warm in all these images, and that is presumably caused by adiabatic heating caused by descending air. So we get rising air at mid-latitudes and then descending in the polar regions. And we will get back to that later in this talk as well. So next we will look at radio wavelengths, which probe deeper in the atmosphere. below the cloud layers, the ALMA at millimeter and the VLA at centimeter wavelength. So now we really go down to almost the NH4 or the basically to the NH4SH cloud layer. So also in 2003, we observed the planet at radio wavelengths with the Very Large Array in New Mexico. So the top row here shows images at 1, 2, and 3.5 centimeter. And the bottom row shows the same images after we have subtracted a uniform limb darkened disk to bring out the fine structure on the disk. So these images clearly show that the South Pole is also much warmer than the rest of the planet, just like at mid-infrared wavelengths. So a complete spectrum of the disk average brightness temperature is shown here on the right, with a solar composition model atmosphere superposed as the dashed black line, which is clearly way too cold. A good match to the spectrum is obtained by increasing the hydrogen sulfide abundance by a factor of 50 over the solar sulfur value, and leaving ammonia at a solar abundance, which is the model shown in red. So these were the key measurements to determine the composition of Neptune's deeper atmosphere. The carbon abundance was basically determined using visible light and near-infrared spectroscopy. So at the pole, which is much warmer, hydrogen sulfide is actually close to the solar value, down to about the NH4SH cloud layer at 50 bar. That is to say, both hydrogen sulfide and ammonia gas over the pole are very much depleted so that we can probe much deeper, warmer layers in the atmosphere there. So in this image, we show more recent radio observations with both ALMA and the VLA, probing again from just below the main methane cloud deck at about 1 bar down to the NH4SH cloud at 50 bar. So these images, also they're much better. They essentially corroborate our earlier findings with a very warm pole. Plus they also show some prominent latitudinal variations across the disk. This all culminates into this general circulation pattern that I showed before, extending from the stratosphere at about 1 millibar levels down to tens of bars in the troposphere. So really here we have rising air at the mid-latitudes where we have adiabatic cooling, so where air is rising, both in the troposphere and the stratosphere we see cooling, and this cooling is seen in the mid-infrared in the temperature. And we see the cooling also because clouds are condensing in the near infrared. So adiabatic heating is seen over a region where the air is descending. So the South Pole and the equator at mid-infrared wavelengths are warm, and these regions are generally relatively free of clouds. And since the descending air is much drier than rising air because the gases have condensed out, deeper, warmer layers in the atmosphere are probed at radio wavelengths, and that results in the enhanced brightness temperatures in the radio over the pole. Well, we wish that it was this simple, but not all the data agree with this picture. So by carefully tracking about 100 cloud features with Keck on 2 nights in H and K bands, that is at 1.6 and 2 micron, my former student, Josh Tollefson, showed that the winds measured in K bands, probing high altitudes near the tropopause, are on average very similar to those measured by the Voyager spacecraft. And that is shown here on the right. The black line is the Voyager wind profile, and the red line, the Keck K-band profile. So there's a large dispersion for different features, however, and that is indicated by the colored bands. So the winds measured in H-band, 1.6 micron, are sensitive to lower altitudes, which are near the methane clouds. They are slower, shown by the purple bands. So the difference between these two bands reveals a vertical wind shear in the atmosphere. And that is in fact opposite to what one would expect on theoretical grounds. So it can be reconciled if the equator would be a few degrees colder than mid-latitudes, but that would only be the case if gas is rising at the equator. and that contradicts the circulation as derived previously. And it may actually imply a so-called double-stacked circulation cell, as shown here, where you have one cell where material is sinking over the equator, and then below it another one where air is rising. So the dark spots that we just talked about, they typically have speeds that are in between these purple and red lines. So in 2017, the same graduate student, Ned Malter, together with a support astronomer, Carlos Alvarez at Keck, developed software for our so-called Twilight Zone project. And that's a project that we envisioned where observing assistants could use twilight time just before the sun would rise, time during which the sky is usually too bright for most astronomers, but it is ideal for snapshot observations of bright solar system objects. So during Ned's first test run on June 26, 2017, they captured a massive storm system on Neptune, a storm about 3/4 the size of the Earth. So it was getting much brighter in the following week. This storm is near Neptune's equator, which is kind of odd because we usually don't see much activity near the equator, where material air is sinking down, is descending in the atmosphere. So this storm was also imaged regularly by the amateur community because it's so bright, they could see this too. And that gave us a wealth of information. Here, for example, is an image from Phil Miles. And many of the amateur astronomers actually contributed images for this project. It was also observed by the Hubble Space Telescope, and radiative transfer calculations using both the Keck and the Hubble Space Telescope showed that the top of this storm is around the half-bar level, so just below the tropopause in the troposphere. The storm was tracked over a period of 7 months. The storm was still visible at the end of July. It had disappeared in early September, but instead we see a string of small cloud features along the equator. Then it was back in October, and it remained visible until at least the end of December. So when we use all the available data from large telescopes as well as the amateur community, that permitted determination of an accurate drift speed of about 200 meters per second, which is a little less than the canonical wind speed as derived from Keck and Voyager data. And that may mean, so here we show this black spot near the equator, that is the wind speed of this bright storm region. These other black spots show the wind speeds of the great dark spots at those latitudes. So this means probably that this bright spot was anchored relatively deep in Neptune's atmosphere. So this string of cloud features that we saw in September, and we didn't see the bright storm anymore, that reminded us of the big storm in 2010, 2011 on Saturn that was also discovered by amateur community. And here we see an image from the Cassini spacecraft. So that such storms on Saturn have been seen about every 20 to 30 years. So it's very rare. And it's thought to be driven by episodic moist convection. That is, convection may be suppressed for decades until it suddenly breaks through into a giant storm. I mentioned before that usually we don't see many storms in the equator where air is subsiding, but in particular in regions where overall the air is subsiding, convective storms may occur. So this storm on Neptune may be one of these very rare events. So with this Twilight program, And our observations, which go back to 1999, we can look at the long-term evolution of the planet. So Wes Lockwood showed that Neptune's reflectivity overall is changing over time, as shown by the blue curves, blue points on this graph, which were taken with Lowell Observatory. So a former student of mine, Andrea Zorzi, superposed Hubble Space Telescope data in red on this graph. So equinox, that is when the equator was pointed at the sun and we see both hemispheres equally, and the summer solstice, the point where the sun appears to reach the highest point in the sky at the South Pole, they're both indicated. And as shown, they are about 40 years apart. So a timeline of images obtained over the years, in part thanks to this Twilight program, show that the overall cloud activity does seem to vary. And that is in particular, well, here we see it from 1999 to 2017. But then if we continue to 2019, we start to see towards the end of 2019, that are just not many cloud features. And that continues into 2020 and 2021. Maybe there are more features now in 2021. So one of my, she was an undergraduate student. She's now in between, well, in her so-called gap year, around the Chavez. She has been looking at the long-term evolution of the cloud coverage on Neptune and its overall reflectivity at infrared wavelengths. So this panel shows a fraction of the disk covered by clouds as seen with Keck and the Hubble Space Telescope. So we see here a clear variation over time. The peak is reached around 2003, just before the 2005 summer solstice. But also as shown in late 2019, there simply was not much activity. I mean, the cloud fraction of cloud coverage is very, very low. And we also noticed in 2017 that there's a lot of dispersion due to this equatorial storm. So we can look also at the reflectivity of the entire disk, as shown before by Lockwood. And we show here the total reflectivity as a function of time, which shows a similar picture of the variability as the fractional coverage by clouds. So seasonal variations that are caused by changes in the subsolar latitude are expected to produce variability in Neptune's temperatures and stratospheric photochemistry. However, such changes should occur over decades-long timescales because Neptune's orbital period is 165 years. And so one season will last for about 40 years. So summer solstice was in 2005. So the period we cover with Keck is all during the summer in the southern hemisphere, moving now into the fall in a few years. So the changes we see happen on much shorter timescales. So it's definitely not caused by these seasonal variations due to the viewing geometry. If the variation is driven by external solar forces, we can look for effects caused by variations in solar ultraviolet emissions, which could affect clouds or aerosols through chemical reactions. So variations in the UV solar flux are shown here in blue in the bottom panel. And you can see that there's a really good correspondence between the variations in Neptune's reflectivity with the UV flux, slightly delayed, as one might expect. So this work is still in progress. So in addition, temperature, of course, is important too. And we can address variations in temperature with mid-infrared measurements. And so very recently, a paper came out where Mike Roman was the first author on observed changes in Neptune's thermal infrared brightness and that provides a measure of the temperature in Neptune's atmosphere. So this plot here shows the relative change in the thermal infrared brightness from Neptune's stratosphere over time, from about 2003 to 2021. Corresponding thermal infrared images are shown at the top at wavelengths of about 12 micron in the ethane band. And they show Neptune's appearance in 2006, 2009, 2018, and 2020. So these data points are taken with many different telescopes at different times, but collectively they show a decline in Neptune thermal brightness since 2003, which was the first time reliable thermal images were taken. And those were the images that I showed you before, and I show you here again. On the right, we show the temperature pressure profile, as well as the so-called contribution or weighting functions, which show which part of the atmosphere is probed at which wavelengths. So basically, between 7 and 13 micron, where we're sensitive to methane and hydrocarbons, like ethane, we probe the stratosphere, the layer in the atmosphere just above its active weather layer in the tropopause. And as shown over the years, there is a huge variability here on temperature. At the longer wavelengths, here at 18 micron, where we are sensitive to hydrogen, we probe the tropopause, and that is where we do not see much variation at all. So the so-called radiative time constants near the tropopause are of the order of 100 years. And so in fact, we do not expect much change in Neptune's temperature. And so the observed lack of variation is consistent with expectations, whereas in the stratosphere, the radiative time constant is much smaller, about a year. And so we do expect time variability. So as mentioned before, the data points in this graph were taken with many different telescopes at different times, but really collectively they show a decline in Neptune thermal brightness since 2003. And this indicates that globally average temperatures in Neptune's stratosphere have dropped by roughly 8 degrees Celsius or 14 degrees Fahrenheit between 2003 and 2018. So we would have expected the stratosphere to reach a maximum in the summer hemisphere shortly after the peak insolation at summer solstice in 2005. So the peak was reached much earlier. And then from 2003 to 2005, we see a decline in the disk average, in the disk integrated stratosphere gradients and implied temperature. The South Pole, however, appears to have become dramatically warmer in just the past few years, by roughly 11 degrees Celsius, and that reverses the previous globally average cooling trend, as shown here at the bottom. That's really all due to this increase in temperature in the South Pole. Well, such a polar warming has never been observed on Neptune before. So one explanation for this apparent inconsistency between seasonal models and observations may be resolved by the feedback between photochemical and radiative processes. While methane absorbs sunlight and warms the atmosphere, it gets photodissociated, falls apart, and subsequent photochemistry produces hydrocarbons, primarily ethane and acetylene. And these hydrocarbons are powerful infrared emitters that serve to cool the stratosphere. So there's a balance between this radiative heating and cooling changes as the amount of photochemical hydrocarbons changes. And that could shift the peak temperature to occur before summer solstice. And moreover, since the observed radiation is sensitive to both the temperature and the ethane abundance, it's not immediately clear if the planet or a region on the planet, like the South Pole, would increase or decrease over time. And that is something that we're still working on right now to try to find detailed explanations here. My guess is we do need more data. After the initial detection of Neptune 175 years ago, we really now have learned a tremendous amount about the planet itself, its rings and moons. But as usual, the more you learn, the more questions surface as well. So we touched on this talk about composition. We haven't really addressed the question, what is the water abundance? Because we really don't know. We talked about the general circulation model, whether it's just one cell where you have air rising at mid-latitudes and descending all the way between the NH4SH cloud and the upper stratosphere, or perhaps there may be double cells. We may have one cell above the other cell, sort of a stacked circulation. We have talked about large convective storms. We don't know how often we can see them. We've only seen it once, these really large ones, nor how they're triggered. We've talked about dark spots, their origin and makeup, maybe. The interesting thing is we saw dark spots during the Voyager era, and then none of them for 20 years after, and then recently we saw a few yet again. We talked about the evolution over time in clouds and temperature. We don't really know the cause of it. We talked about the stability and evolution of wing arcs and the composition of the various moons. So in the future, in the near future, we have the James Webb Telescope, and with the James Webb Telescope, both planets, Uranus and Neptune, will be observed. And further into the future, NASA's Decadal Survey just announced that their first priority is a flagship mission to Uranus with an orbiter and a probe. So there will be perhaps answers to some of our questions, and no doubt more questions later on, once this Uranus orbiter probe will be there. But if I will see that, I kind of doubt. That will probably be in 2050 or so. With that, I'd like to close the talk.
Thank you so much, Professor. That was a very interesting discussion. I was wondering if there are any questions from the audience. Please feel free to unmute yourselves or paste in the chat window. Okay. If not, I have a couple of questions. So I did see that I think most of the measurements were kind of taken around like October to December timeframe, like every year. I was just wondering if there's like a specific reason for measuring around that time frame, or it's just like.
Well, we have to. I mean, most of these were taken with ground-based telescopes, so it has to be night. So that's heavier, and then we typically try to get time when we can see both planets for at least half a night on the Keck telescope, and that kind of puts us into this time frame, sort of August through December. But there are also, I mean, images that were taken during this Twilight program that were at different times.
Yeah. Thank you. Okay, I had another question. So I think you were mentioning about the cloud cover, and I think there were like years when probably there wasn't as much activity. So I was just wondering if it's got to do anything with like the tilt in the orbit. So probably the orientation is not like the same or like many years. I mean, I guess it kind of keeps changing. I was just curious if that somehow affects the cloud cover, or maybe not.
No, the changes are very slow over time. And as I show kind of here, where we see the refractivity of the clouds in the top panel, we really see that in this past few years, I mean, there was very, very low activity. And we think that the most likely explanation, but we're still working on that, is that it's driven by the solar flux. And this here is the solar Lyman alpha emission. And you can really see that, I mean, there's a very similar pattern in the UV flux and the cloud cover. And that can be explained by basically photochemical reactions of the UV sunlight triggering or not triggering the cloud formation.
Yeah. Thank you. Yeah, and I think you mentioned about I think the moons of Neptune. I do know, like for Jupiter, probably initially they, I think a couple of years back, they thought there were like 56 moons or so, and they've been discovering more and more. So I think for Neptune, so far there are like 14 moons discovered. Yeah, I was just wondering if there's like any chance that there could be more, or yeah, I'm not sure if like your team is focused on that as well, like discovering moons of Neptune to kind of help study Neptune itself further.
I mean, yeah, so the moons that you're referring to are these so-called irregular moons at large distances from the planet. And I mean, there surely can be more moons to be discovered around Neptune. Neptune is far away, so the moons are very, very faint. So it's much harder to detect them around Neptune than around other planets. So there may well be more.
And yeah, I assume like Uranus and Neptune, I think you did mention briefly, they have like different composition. I mean, they're more like ice like planets rather than Jupiter and Saturn being more like gas giants. So I was wondering like if the composition is kind of similar for like Uranus or Neptune, or it's like totally different. I think you did have a slide explaining a little bit of it, but probably, yeah, I mean, still.
Yeah, so indeed, the composition of Uranus and Neptune is very similar.
Yeah.
So both Uranus and Neptune are have about 80% hydrogen, 15% helium, we think, and methane gas on both of them is enhanced by a factor of, well, between 60 and 100 over the solar carbon value. And also hydrogen sulfide is what we have seen with using the ALMA and the Very Large Array observations is very similar for the two planets, with an enhancement over the solar sulfur value of about a factor of 40. And then ironically, ammonia is much, much less. It's about the solar value. So those are kind of intriguing discoveries in a way, and that we think is probably tied in with the formation and evolution of these planets. So basically with the, well, I always try to think about the planets formed, at least the core formed, from accretion of so-called planetesimals or building blocks. And they can come, of course, from anywhere. They can easily migrate throughout the solar nebula. But these planetesimals probably consist a lot of sort of crystalline water ice. And if you have this crystalline water ice, they can trap in kind of cages, they can trap other volatiles like H2S or ammonia. And that process is not equally efficient for all the different molecules. So in fact, it is much more efficient to trap molecules with carbon. Basically, it's in the form of CO, carbon monoxide, than nitrogen, for example. And also H2S it's more efficient to trap those molecules than N2. So if the planetesimals are made of this crystalline water ice, then there can be huge differences between the various molecules or elements compared to the solar values. So for Jupiter, all these molecules are enhanced by roughly similar values between a factor of 2 to 5. I mean, they don't differ all that much. Mm-hmm. And so one of the early ideas was that Jupiter was made up of planetesimals where the water ice was in what they call an amorphous ice, which really forms at very, very cold temperatures. But I mean, Jupiter can probably explain this other type of ice as well. Now, one of the things that people really are eager to find out is what the water abundance in these different planets will be, because the water abundance will really kind of show whether or not the water was in this crystalline form and trapped these different molecules. If that is the case, if it's those planetesimals that made up the planets, then the water abundance should be should be 3 to 4 times more enhanced over solar than the methane abundance. So we would expect for Uranus and Neptune, we would expect a 300-400 times solar oxygen value for the water abundance. But that is really hard to measure. So, because you can send, I mean, they will send a probe to Uranus, but this probe has to go down to a few hundred bar level in order to really measure what the water abundance is. And that is just not possible. Another thing that is important to figure out how these planets and where they formed is to look at the noble gases. And so for Jupiter, that has been measured with the probe. And so for Uranus, they hope to measure those gases also with a probe. And there you can measure them at the few bar level and you get a good measure. And that will already give us a lot of information on these building blocks of the planets.
Thank you so much. Is any questions from the audience? Okay, looks like not. Then I think we can conclude the presentation here. Thank you so much, Professor, for this wonderful presentation. I think we all would agree that we learned a lot about, like, Neptune, like over the years, discovery. Yeah, it was really great. And I'd also like to thank Tinka Ras, the founder of NTAP. And thank you, Zoom audience, for being a part of tonight. Our next talk is on June 4th by Lynn Kominsky, and the topic is Gravitational Waves, the discovery that won the Nobel Prize. I look forward to seeing you all again. Goodbye for now.
I'd like to say goodbye as well and to give a special thank you to our speaker, Imke. It was a wonderful talk with a lot of information for us to digest. And we really appreciate your coming and sharing it all with us. We don't have a way of clapping, but what we do is we raise our hands this way. So if everybody would just like to give her a little wave to let her know how we've appreciated her talk. Thank you so much, everyone. And don't forget to get a good look at the eclipse tomorrow night and enjoy the night sky.
Okay, thank you for the invitation, Tinka. And I hope even though it was a lot of information, I hope that it was kind of digestible.
Definitely was. Thank you so much.
Thank you so much.
Not quite the same as having you up on the mountain, but it's better to have you, even if it's just virtually. And we really do appreciate the time and effort you put into this presentation for us. Thank you.
Hey, thank you.